So in this video, we're going to have a discussion about sign charts, specifically sign charts for f prime of x. I want to make sure we really try to talk about why they work. That's, probably one of the biggest issues I see students having. Like they can do the problems that involve sign charts, they can build them, they can develop the conclusions with them, but the logic behind why they work is sometimes lost. So I want to make sure we talk about that. And then, of course, we'll get into how to build one and then how to use one. This is what they look like. We'll take some time to build this in just a few minutes. Here is a graph, kind of a crazy looking graph. We've got a graph that has a minimum, local minimum here, and another local minimum here. Check out what's happening as we pass through the x value of A and the x value of C. The slope of the tangent line on this stretch of the graph is negative. It's 0 at A, and then we come out on the other side of A and we have positively sloped tangent lines. Same transition happens at C with a slight change in what's happening at C. We have negative slopes to the left. We do have positive slopes to the right. Now what's happening at the x value of C, the derivative is not equal to 0 like it was at A. The derivative is undefined. Check out the other two locations here where we have local maxes. We have positive slopes to the left of the local max. We have negative slopes to the right. Positive slopes to the left, negative slopes to the right. What's happening at the local max? The derivative has a value of 0 at B, and the derivative has a value that's undefined at D. If your derivative changes signs from positive to negative or negative to positive at a point that's on the graph, what you're guaranteed to have is a local max or a local min. Now, how the change happens, negative to positive, positive to negative, dictates whether you have the max or the min. What needs to happen in order for the derivative to change signs? One of two things must happen. Either the derivative would have to equal 0, the derivative is equal to 0 at A and B, and we have a sign change in the derivative at those locations, or the derivative needs to be undefined. This derivative is undefined at C and D. We also have a sign change in the derivative as we pass through those locations. Now I have the conclusion here that we kind of went through verbally as we were looking at this graph. This question is pretty easy to answer with the graph. When you're looking at the graph, it's pretty easy to say, yeah, local max, local max, local min, local min. When would you need to use a sign chart in order to develop this sort of conclusion? What if you don't have access to the graph? What if you're not allowed to use a calculator or Desmos? What if it's on you to do the analysis by hand in order to develop the conclusions about local maxes or local mins? So extrema would simply be a term that refers to both of those with a single word. So we want to find the local extrema of this function. What if we wanted to figure out where the function was increasing and where the function was decreasing? That's also something that we could have done back here. Function's decreasing where we see those negative slopes, it's increasing where we see those positive slopes. Decreasing, increasing, decreasing. So both of these questions are pretty easy to answer if you're staring at the graph. What if you're not staring at the graph? Now, the directions here, the prompt here says find the critical numbers. Critical numbers refer to the two types of locations that we highlighted on this graph. Critical numbers are either places where your derivative is equal to 0, or they're values that are in the domain of the function where your derivative is undefined. The only way that the sign of a derivative can change is if it first passes through the value of 0 or first passes through a location where it's undefined. I can't have the sign of the derivative change from 1 to -1 unless I make a smooth transition and pass through 0 sometime in between, or unless I instantly change from that, I think I went positive slope to negative slope, right? 1 to -1, unless I instantly change and pass through that location where the derivative is undefined. The derivative has to be 0 or undefined before the sign of the derivative can change. We're going to try to answer this first question. Find the critical numbers. Again, critical numbers are locations where the derivative has the opportunity to change signs. Places where it's equal to 0, places where it's undefined. We'll do the local extrema part first, and then we'll actually use the same work to develop the secondary conclusion as well. So here is my function. I'm going to take the derivative of that function. Critical numbers are locations where your derivative is either 0 or undefined. So I take my derivative. I'm going to set that derivative equal to 0. I'm solving this by factoring, so I've removed the common factor of 6 from everything just to make my trinomial factoring a little bit easier. So this is how the trinomial would factor. This factor is equal to 0 when x is 2. This factor is equal to 0 when x is negative 1. Here's the sign chart. How do we build it? We're going to start the sign chart with a number line. Number line. That number line should represent the domain of the function. This function's a polynomial. This function has a domain negative infinity to infinity. So I literally just have a number line that extends to negative infinity that direction, positive infinity this direction. What I'm putting on that number line is I'm plotting my critical numbers. Why am I plotting my critical numbers? We said this as we were looking at that graph a few minutes ago. The only time the sign of the derivative can change is if my derivative is first equal to 0. Here are the x's where that happens, or my derivative is first undefined. This derivative is never undefined. We don't have any of that sort of location to go into this sign chart. This derivative has exactly 2 opportunities to change signs as we pass through the x of negative 1 and as we pass through the x of 2. If I determine that the derivative is positive at negative 2, I know that it's still positive at negative pi and at negative 5 and at negative 5 million. If I determine that the derivative is negative at 0, I know it's still negative at 1 and 1.5 and 1.9 and 1.99. The only 2 opportunities the derivative has to change signs is as we pass through these 2 critical numbers that we've already identified. So I'm going to pick a test value from this stretch of the number line, see what the sign of my derivative is. If I know that it's positive at negative 2, I know it's going to remain positive at negative 5 million. I'm going to pick a test point from this stretch of the number line, and I'm going to pick a test point from this stretch of the number line. So these critical numbers basically divide your sign chart into different intervals, and whatever you determine the sign of the derivative is on one of those intervals, it's going to remain that sign throughout that entire interval. So what I've done down here is I've said, okay, I'm going to think about f prime of negative 2. So if I pick negative 2, which would be located here on my number line, I'm plugging into this factored form of the derivative. 6 is just going to remain 6. Negative 2 minus 2 is negative. Negative 2 plus 1 is negative. I know I'm looking at a 6 times a negative times a negative. That multiplies together to give a positive. I don't care about the numerical value. I just care about the sign of the derivative. Similarly, I'm picking 0 as my test point from this next stretch of the number line. And if I put 0 in place of this x, 0 minus 2 is negative. 0 in place of this x, 0 plus 1 is positive. Positive, negative, positive, multiply together to give a negative. And then if I pick a value like 3, and I don't have to pick 3, I could pick pi, I could pick square root of 10, I could pick anything that's on this interval of the number line. Be nice to yourself, pick something that's easy to work with. When I pick 3, this is going to be positive in this set of parentheses. This set of parentheses will also be positive. Multiplying 3 positives together gives me a positive result. So what can I say as my conclusion here? Well, what I can say in conclusion is since f prime of x is greater than 0, since f prime of x is greater than 0 to the left of x equals negative 1, and f prime of x is less than 0 to the right of x equals negative 1, f of x attains a local maximum at x equals negative 1. Right? If my graph is going to go from positively sloped to negatively sloped as I pass through this x, I have to have a local max at that spot. What I can say about 2 is since f prime of x is less than 0, if I could type, to the left of x equals 2, and f prime of x is greater than 0 to the right of x equals 2, f of x attains a local minimum at x equals 2. Now, if you're wondering why I wrote out what I wrote out here, can I just write the conclusion, local max at x equals -1, local min at x equals 2? You're going to have to listen to your professor, listen to your teacher. I teach AP Calculus. In AP Calculus, we have to verbalize the logic that we apply to a sign chart in order to get full credit in a free response question on the AP exam. So that's why I've written out what I've written out here, verbalize the logic that goes into the conclusion, not just made the conclusion. Just pay attention to what your professor, your teacher is asking you to do and act accordingly. One more screen here, so we'll click ahead. And for the same function, determine the intervals where f of x is increasing and the intervals where f of x is decreasing. This is the same exact sign chart. I know my derivative is positive from -infinity to -1. It's positive from 2 to infinity. My function is going to be increasing on those intervals. Now notice I have included the endpoints here. I'll probably try to put together another video that tries to go into some logic behind why that's able to be done. But since the derivative is greater than or equal to 0 on these intervals, it's never negative, I'm increasing on them. And since my derivative is less than or equal to 0 from -1 to 2, my function is decreasing on that interval.